In this podcast, we're going to talk about properties of molecular solids and properties of covalent network solids. All right, first let's start with molecular solids. These are just molecules or noble gases, so basically just covalent molecules that are not going to be in a network. And they have relatively weak intermolecular forces. Some examples of molecular solids are going to be H2O, CO2, CH4, NH3, NO2, CO, C2H6, C2H5OH, C6H12O6, alkenes and alkanes, which are hydrocarbon groups, diatomic molecules, so that's the special 7, and the noble gases. Some properties of molecular solids are they have very low melting points and boiling points. Usually we are going to see them as gases or liquids because they've already melted and boiled. And they are poor conductors of electricity because they're individual molecules and you have no ions or mobile electrons to aid in the movement of the electricity. The reason that molecular solids have a low melting point is because they have very weak intermolecular forces. So we know that they can have, all of them will have London dispersion, of course, and then they can also have hydrogen bonding and dipole-dipole, but that's all they can do. So those are considered very weak intermolecular forces as compared with ion-ion interactions, and then you get into the intramolecular forces, covalent bonding, ionic bonding, metallic bonding, which we know are a lot more. So molecular solids have the lowest melting points because of the lack of intermolecular forces present here, not holding them together. Sometimes we see molecular solids as very large molecules, or what we like to call polymers, which means a long string of molecules, and they can have important commercial and biological applications. So here we see a polymer down here. It's showing you the individual units that are present in the polymer, and this can be hundreds of thousands of strings long. Proteins in our body are made of polymers, long strings of molecules, and they're all folded together into this special shape, and what gives them their special shape is the intermolecular forces that occur between all the chains, and that's a very important thing because without that our body wouldn't function the way it does. Another thing that polymers are plastics. So you know that we have plastic all over our society, so we use polymers in plastics all the time. So that's a very important commercial application. All right, so that was just molecular solids, which are the individual molecules. Now let's talk about some covalent network solids, which form a network, which is more of a three-dimensional structure. Sometimes you get two-dimensional structures, as you see with these sheets of graphite over here. And all of these are held together with covalent bonds. You can have covalent bonds that are covalent network solids that are elemental, meaning they only contain one element, such as carbon in diamond or graphite, or silicon, as you see in computer chips and such. Or it can be two different nonmetals. So like SiO2 can be quartz, sand, or glass depending on the arrangement of the network. Silicon and carbon, tungsten and carbon, boron and nitrogen. So those are some examples of network solids. Network solids are going to have highest melting points and boiling points because they are very hard substances. And because they have all of those covalent bonds holding them together. They're also poor conductors due to the fact that they have extended pi systems, so delocalized pi bonding that allows them to bond together very tightly. And because of that, these electrons are not available to help conduct electricity. They're also very good insulators because they're poor conductors, so they tend to not allow the movement of heat. So that makes them a very good insulator. The properties that we've just talked about are a reflection of their structure. So the high melting point is because all of our atoms in a network are covalently bonded. And the three-dimensional structures tend to make them more rigid and hard because they have bond angles that are fixed because they're covalent bonds. Generally, covalent network solids are in the carbon group because carbon has the ability to form covalent bonds, as does silicon. And you see here an example of a carbon atom forming a beautiful diamond. And then you see a different structure of a silicone covalent network solid. All right, graphite is an allotrope of carbon. So it's basically just a bunch of carbon atoms that all form together into sheets, and they make these two-dimensional networks. So they all form together, and you get these sheets. There's two different pictures here, and then these sheets have interactions between them that hold them together. And here you see this shiny structure that we get down here that actually is graphite. Graphite's going to have a very high melting point because of these covalent bonds that make each layer very, very strong. But because of the structure, graphite is soft, and because the layers are able to slide past one another relatively easily. The major forces of attraction between the layers are just going to be London dispersion forces, which we know are the weakest intermolecular forces that you can have. So the graphite does slide past each other very, very easily, even though the individual sheets are bonded very tightly. Silicon is another common element you see in covalent network solids, and it's also a semiconductor. It can form a three-dimensional network similar to what a diamond would do. Silicon's conductivity increases as the temperature increases, so if you get silicon at a high temperature, it can conduct electricity very well. And this kind of brings us to how we can manipulate silicon to do what we want it to do. So we can dope it, is what they call, where you insert other atoms into your covalent network, and depending on what type of element you insert depends on what type of properties you're going to get from the material. So N-type semiconducting or N-doping, as it's often called, is when you add an element that has an extra valence electron that carbon or silicon does not have. Silicon's usually what we're working with here, though. This means that we could be using something like phosphorus, something that's more on the right side of the table. This is going to make that semiconductor have a negative charge, because we know that the more right we get on the table, the stronger the electronegativity, and therefore the more they want electrons. We can do the opposite by putting in a element into the network that has one less valence electron than silicon. This is called p-type semiconducting or p-doping, and this will cause the material overall to have a positive charge. So here's a picture that shows us we have N-type and p-type silicon. Alright, so up here we have a covalent network that has phosphorus atoms, and we know that phosphorus is more electronegative, so we're going to carry negative charges up here. Boron has less electrons than silicon, valence electrons, and so this down here is going to carry a positive charge. So we have a positive charge on the bottom and a negative charge on the top. Now, the junctions between the N-dope and the P-dope material can help us control electron flow, and therefore this is the basis of modern electronics. Okay, so we have this P-N junction, which is where we see the positive carrying material and the negative carrying material meeting, and we can control electronics through this junction. Okay, so you see that covalent network solids and molecular solids have many uses and properties that are related to their structures.